Hello, I'm Katie Steckles.
I'm Peter Rowlett. What's our mathematical object?
Today our mathematical object is a pencil.
Okay, good object for doing maths with.
Yeah, well that's one of its many uses. So I wanted to kind of chat about the maths of this, I guess, a little bit, but it's more strictly about the maths of chemistry. Which, given that a pencil is just a sort of regular everyday object, everything's a chemical, kids, don't forget. So a pencil is made out of atoms, as are all things. And it came to me when, a little while ago, I was doing a show about chemistry. For some reason, as a mathematician, I was roped into this periodic table themed, I guess it was a variety show, I suppose. So they thought, okay, let's put some maths in there. And one of the things that I was doing was talking about the maths of chemistry, so the way that chemists use mathematics. And one concept that's really crucial is the idea of a mole. And if you remember any vague chemistry from school, you might remember that a mole is a number of atoms of a substance. So it's Avogadro's number, which is 6.022 times 10 to the 23. Which I did memorise because I was that kind of kid. And it's that many atoms, but it is also a kind of a mass of an object, which is equal to the mass of 12 grams of carbon-12. Okay. So carbon-12 being a particular form of carbon that has an easily measurable mass. And they've picked the value of a mole such that it is exactly the same as the mass of 12 grams of carbon.
Okay. And why is that needed? Why do we need this unit?
Well, it's because it's essentially a number of atoms rather than a particular mass, because obviously different molecules have different weights, so the substances have different densities, and if you want to have a reaction between two substances, you want, however many atoms of this to react with however many atoms or molecules of this, because they react in pairs or in 2-to-1 or whatever ratio it is. So you need to know how much of each substance to put in, because otherwise you'll end up with lots of substance that doesn't react. So when you want your reaction to happen properly, you want to make sure you've got the right amount of each chemical, and you'd have the same number of moles of each rather than having the same mass in grams of each.
Yeah, so it's sort of, you can't measure a bunch of atoms, you can only measure the weight, but measuring the weight means you've got to look up a bunch of stuff, but this makes your calculations easier.
Yeah, so it's like a different unit, but it kind of removes the need to worry about the density or the whatever. You just calculate the number of moles of something. And I think it's lovely. I think it's a really nice idea, because it essentially just means that chemists have to do loads more maths, which I'm in favour of. But I was basically thinking, I'm going to have to go on stage and explain what this is, but even though I intellectually know that a mole is 12 grams of carbon's worth of atoms, how much is that? So if I have like an everyday object like a pencil, how many pencils is 1 mole of pencils? Basically, was the question I wanted to answer. And I was kind of sitting backstage at this science festival. I was thinking, I wonder if there's an object in this room I could take on stage with me that is 12 grams of carbon. So I started working it out for a pencil using a pencil. So I thought, how much carbon is in this pencil? And it's kind of an interesting question. So I'm going to do some working out on paper here, and we'll post a photo of this alongside the podcast, but you can imagine your own maths along with this. So I didn't have a weighing scale with me because I happened to be sitting in a green room at a science festival, but I did have a ruler. So I measured the dimensions of the pencil to work out the volume. There's a few stages to this calculation.
This piece of paper is not an envelope, but it is very back of the envelope.
Yes, this is going to be quite rough, I think. So I'm measuring this pencil. I'm going to say it's roughly circular and has a diameter of about 7 millimetres. And it has a lead in the middle, which has 2-ish millimetres diameter. And the length of the pencil, I'm going to estimate I'm going to precisely measure is about, I'm going to say 17 centimetres, taking into account the fact that the end of it is a cone. So 17 is somewhere between the bit where it starts being a cone and the end of the cone. And I'm going to say that's the length. If it were square, that volume would fit into...
You've misused the word precisely measure.
I'm going to imprecisely measure and guesstimate that it is 17 centimetres long. So that means we've got volumes. So the volume of the pencil, the whole thing, is going to be pi times 7 squared times 170, which is the length in millimetres, exactly 170. And then the lead itself is going to be pi times 2 squared times 170. And the amount of wood in the pencil is going to be the difference between those two things. So it's going to be, that minus that, I guess.
So you've got a cylinder, which is the whole thing. You've got a cylinder in the middle, which is the lead, and
Yeah.
the wood is the bit that isn't the lead.
Yeah.
If that makes sense.
So I may or may not be using a calculator right now. So 49 pi times 170 is about 26,169.4
Definitely.
millimeters cubed.
The measurement you did definitely warrants that
Yeah,
extra
defo,
decimal
yeah.
place. Yep.
And 4 pi times 170 is 2,136.3 millimeters cubed. So those are our volumes, and then the difference is going to be the amount of wood. It's 26169.4 minus 2136.3, and that is 24,033 millimeters.
0.1. I mean,
one,
you
of
can't
course.
forget the 0.1.
So, 0.1 of a cubic millimeter is a significant amount of wood. So that's wood only there. So I don't know the mass of the pencil, but I do know the volume of the pencil, and I have Googled the density of both wood and graphite, which is what the lead is made of. So the density of wood is, the density of cedar wood specifically, which is what most pencils are made from, is about 0.38 grams per cubic centimetre. So I'm going to have to do a unit conversion on those cubic millimetres. So what do you reckon, 1,000 cubic millimetres in a cubic centimetre?
Yes.
Yeah, let's go with that. So
I find unit conversions ridiculously hard for some reason.
So I need to divide this number by 1,000. That makes sense.
I think we're getting close to...
I need to move the decimal point 3 places to the left.
I'm sure that's how people like you to think of it.
Okay, so let's do that. Yeah, that's definitely how it works, kids. Don't forget. And this one is 2 cubic centimetres. That seems reasonable. 2 cubic centimetres for the volume of the lead of the pencil. I'll believe that. All of this is I'll believe that level maths.
Yeah,
here.
there's a combination of knowing different units and visualising volumes and everything here, and a bit of arithmetic, and it's just completely outside of my
so
familiarity.
The volume of the lead is 2.1-ish centimetres cubed, and the density of graphite is about 2.3 grams per cubic centimetre. So that'll give me a number of grams for each of these things. So 24.0331, very important, times 0.38 is 9.13 grams of wood,
right.
I think is what we're saying. And I mean, I could just round all of these to the nearest 10. This is nonsense. But 2.1363 times 2.3 is about 4.9 grams of lead, which makes sense.
Okay.
I'm calling it lead, but it's not lead. It's pencil lead. I'm going to put pencil lead. Now, the weight in grams is one thing, but then the question is how much of that is carbon?
Yeah.
Because not all of these things are 100% carbon.
At this point, we can say your 4.9 and your 9.1 is about 14 grams. Does that feel like it's about 14 grams?
Yeah, and I would believe that this pencil weighs about 14 grams, so we're on the right track.
Yep.
So of my 9.1 grams of wood, I've checked again by looking it up online, and wood is about 40% carbon in terms of the actual atoms that make it up. Okay. So 9.13 times 0.4 is 3.65 grams of pure carbon. And in the pencil lead, I mean, as much as everyone would love to have you believe that pencil lead is 100% graphite, which is the substance that's made entirely out of carbon atoms, I found on the Steckles website, where they make pencils, they have listed the compositions of their different pencil types. So it actually now depends on what hardness of pencil I have.
Because that makes total sense.
Yeah.
If all pencil leads were 100% graphite, what would make some of them softer than others?
Yeah, so the way they make pencils softer is by replacing some of the graphite with clay. And I think a bit of wax as well. So on the Steckles website, it claims that for, this is an HB pencil, so for an HB pencil, 68% graphite
Okay.
Which does throw the calculation that I've just done to find the mass of it completely off, because obviously that was not pure graphite. But anyway, let's assume the density of graphite and clay is roughly similar to the density of graphite.
Okay.
So if this one is, we're saying, I'm going to go with 70% carbon, then the 4.9 grams of pencil lead times 0.7 is going to be about 3.43 grams of pure carbon.
Okay.
So in total, we have 3.65 plus 3.43 grams of carbon, which is, didn't zero the calculator, 3.43 grams of carbon, which is about 7.08 grams of carbon. So it's not quite 12. But I think, this will obviously vary massively between pencils and how much rounding you do. But in terms of orders of magnitude, it's between kind of a half and 1 mole, right? So if we're talking about what is 1 mole of carbon, what is 1 Avogadro's number of carbon atoms?
That was 12 grams. Right?
Yeah, it's 12 grams.
Yeah.
So assuming there'll be a bit of wiggle room in this. I mean, the choice to do this calculation live was a pretty bold one. So when I did this backstage, I got something like 10, 11 grams, and I was like, that'll do.
Yep.
So I've realised that, I mean, because obviously there's a rubber on the end of here, there's a ferrule made of metal, like there's no way we could know exactly how many carbon atoms are in here. The paint probably has some carbon in it, because some of it's black paint, so maybe that's carbon. But
Depends how new the pencil is as to how long it is.
Exactly, and how much I've sharpened it.
Yeah.
Although I did measure the length, but anyway, something like on the order of magnitude 1 mole in a pencil, which is a really nice little fact. And I proudly stood up on stage and held up a pencil and said, this is about 1 mole of carbon. But it really contextualises it for you, I think, as a quantity.
Yeah.
And it's also, like, if you're a chemist, 1 mole of something presumably roughly will mostly look about the same size as a mole of carbon. Some things are heavier, some things are lighter. 1 mole of a gas will be a lot.
Right, yeah.
But 1 mole of any kind of solid substance, it's about the quantity that you'll be working with in a lab, I guess. So it's sort of nice to have that as a physical implementation of that idea.
Yes. Good. So I guess as you were doing this calculation, we sort of joked about the 1 decimal place degree of accuracy, but how close you were holding that thing up to the ruler did not warrant that many decimal places.
Yes, so, yeah. Well, I guess because this is the kind of calculation that sometimes you end up doing just to check whether something's roughly right and whether you're in the right ballpark order of magnitude for something. And a lot of the time people measure things to a precision and write down things to a precision that's completely unnecessary. And my calculator probably stores pi to a lot more digits than it actually needs to, given that you can calculate like the size of an atom to within, or the size of the universe to within the width of an atom using something like 20 or 30 digits of pi. Like, it's not many at all.
I don't think it's that many.
It's probably less than that, but you don't need that much precision on these things, partly because I've googled the density of wood, or I've googled the proportion of it that's carbon, but that will vary also from object to object. So whether there's knots in the wood and that kind of thing will affect it. So I know that none of these calculations are going to be fully precise, so I'm just looking for something that's kind of ballpark. Yeah,
you wanted to be able to say this pencil is 10 moles, or this pencil is 10 pencils would be 1 mole, or whatever you want to say. You just want some sort of approximate figure. Yeah,
it reminds me a little bit of, I remember at undergrad we did a module on, like astronomy and the maths of space. Right. And a lot of that was like, it's about 10,000 or it's about 100,000, and they kind of just didn't care a lot of the time. At one point, I think pi was 10.
Okay. So the important point really is that depending on what you're approximating, these particular precisions don't really matter. It might be absolutely fine to say that pi is 10.
Yeah, well, on the scale that they're working at, things are such huge distances apart that, being out by a couple of meters is completely irrelevant. So, but yeah, it's sort of useful to check whether, like, obviously if you're doing precise calculations for, like, engineering purposes, you need to be precise about these things. But if you just want to know, is it 10 times further away or 100 times further away, then it's absolutely fine.
So Rob Eastaway has a book called Maths on the Back of an Envelope. And one of the things he talks in there is about unnecessary levels of precision and how you sometimes sort of trick yourself into thinking something's more accurate than it is, then because you've got all these extra decimal places that make it look fab when actually it's not
and
justified.
Like as soon as you introduce one other thing that hasn't been measured precisely, then all of that is completely meaningless anyway.
Yeah.
Like it can affect the final answer enough that it doesn't matter that you were super precise with everything else. So.
Yeah. And one of the things I like about Rob's book is I teach our first year mathematical modelling here, and we do a bit of this sort of approximation and estimation and sort of making assumptions. And there's an area called Fermi problems, which is kind of unknowable things that you can make a good estimate of, basically.
Yeah, so it's Enrico Fermi, right, the physicist. I think the reason they're called Fermi problems is because he once estimated the magnitude of an atomic blast by the distance that a bit of paper was blown by the blast.
Yes.
Like he was stood sufficiently far away from it that he just felt like a breeze.
Yeah.
And he calculated based on how far away he was and how far this bit of paper moved, what the magnitude of the blast was, to within like a reasonable accuracy as well. Which is, but
So we give students these sort of questions that you can't sort of like, I mean, how many cats are there in Sheffield, because we're a university in Sheffield, or, you know, how many books are there in the Sheffield Hallam University Library, or whatever it is. We have a bunch of these sort of questions. How many trains pass through Sheffield Station in a day, things like that.
Yeah.
I don't think they're all Sheffield, but that's what's coming to mind. But the point is that some of them you could, I suppose, go and measure, but you sort of wouldn't. But it gives you an idea of a rough feel for these things, and they often feel like problems that you can't possibly go about trying to answer, but there are some techniques you can do to sort of come up with a rough guess that tends to be good enough for most purposes. And particularly the case we use is if you want to say whether one number is about the same order of magnitude as another, or whether one's much bigger than the other. So, you know, are there more panes of glass in a city, or are there more cats in that city, or something?
Yeah.
I mean, it's nonsense stuff, right? You don't really need to know the answer to that, but it's good to practice approximations.
Well, I think often they're used for like interview questions. You hear about these, difficult Google interview questions or whatever that they want you to, like, they throw these at you in the interview, and there's no way you can go and look up, the average number of cats per person in a city or whatever, but you can at least think about how many people have cats and try and use that and that kind of thing.
Yeah, and they're often they don't really care about the answer, they want to see how you think about a problem. And I think this is something that we have a little bit with our students, because they arrive and they go through what we put them through in the first term, and they often sort of think, well, I'm not collecting a booklet of maths notes, therefore I'm not really learning anything. But they're getting better at thinking as we do all these problem-solving exercises and estimation and things like this. And we had this really nice comment once where a student wrote, well, I haven't collected any notes, so I don't feel like I've learned anything this term. However, I have noticed that my approach to problems has improved. And you sort of think, yes, that is what we were doing.
Yeah. Well, I guess the implication of the fact that this is an interview question is that they're expecting you to use those kinds of problem-solving skills in the job.
Yeah.
And I guess, if you're, doing something, you're like, are we going to have enough of these to last the year? It's much better if you can get out the back of an envelope and work out whether the answer is probably yes or probably no, rather than having to actually do a more detailed analysis.
And to take a lot of time to do it. Or, if you've tapped some stuff into a calculator, can you tell quickly whether you're approximately right? Because sometimes you've missed a decimal point or something and you're an order of magnitude out.
Yeah.
And you hear stories about plumbers who want to, miles of copper pipe to, I suppose,
Yeah.
kilometres of copper pipe. Or...
I can't remember what it's... there's a calculator called the Qama calculator, Qama. And it's got this really nice feature that there's a mode you can set it to where you type in a calculation and you press equals and it goes, what do you think? And it won't give you the precise answer until you give it a rough estimate. Yeah. And depending on the size of the number that you're looking for, it'll be within a certain percentage of the correct answer.
Yeah, you can't just put in one every time.
Yeah. But it wants you to sort of, okay, well, that 29 is about 30 and, 14 is about 15, so it's probably about this.
Yeah.
If I multiply them together or whatever. Give them something that's in the right ballpark, and then it will give you the precise answer. And I love the idea of that, just as a tool to force you to actually have a sense of number and a sense of proportion of how big things are going to be.
Yeah.
Because that's the skill, isn't it? Is to be able to go, is it?
Yeah.
There's no way it's that.
Yeah.
Oh, I did it wrong here. That's the skill.
Definitely.
Yeah. I mean, 7 grams of carbon in a pencil seems probably plausible, so I'm going to go with that. Excellent. So we are both on Twitter as I'm at Steckles.
I'm at Peter Rowlett. We both blog at a blog called The Aperiodical, which is the letter A followed by the word periodical.com.
And if you want to get in touch about the podcast, or if you have an idea for an object that we could do a podcast about, or any comments or feedback on any of my maths or anything else in the podcast, you can email us using objects@aperiodical.com.
The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.